Welcome back to the lecture series on GPU architectures and programming. So, I believe in the last week's lecture we have been talking a lot about OpenCL as a programming model and language which is kind of runs parallel in compute capability of CUDA with some differences in terms of application platforms. So, this week we will just continue a bit on using OpenCL for a heterogeneous computing environment. Although I would say that although we will be talking about OpenCL in heterogeneous computing, but realizing that CUDA is also the compute language which is used more often than not, we will also talk about how CUDA programs can be written in such a way that you can have multiple GPU devices on which the program runs, given that some host CPU is orchestrating these different devices. So, starting with that motivation, so just want to say that in this case, if you want to recap, you can just look into the lectures we did earlier on introduction to OpenCL, the details of the runtime system and the different synchronization primitives in OpenCL. So, coming to heterogeneous computing, what fundamentally is heterogeneous computing? So, essentially we are talking about compute platforms which have got more than one kind of devices. It may mean processors, or at a light level we can talk about multiple different cores, because I can have a compute platform with multiple different cores, and each core is kind of optimized to do different kinds of processing. I can also think of a compute platform where on the PCI bus I have different kinds of devices which are attached, and they together are being also attached with a CPU device in the PCI attached in the PCI bus, and which is kind of orchestrating the execution of different kernels in this set of different devices. So, the idea of heterogeneous computing is that how to make good use of this heterogeneity in terms of working platforms to gain in performance as well as energy efficiency. So, if I have to do that, then I need to have multiple application kernels which are executing concurrently in these different devices. So, for that OpenCL is conceived as an ideal programming language because it supports programming across multiple compute devices like CPUs, GPUs as well as FPGAs provided from different vendors. Of course, the vendor needs to support OpenCL ICD loaders, essentially the implementation of the original OpenCL specification that has to come from the vendors, and there are a lot of vendors in recent times who have subscribed to these ideas. Just to let you know, in modern days there has been an evolution in the OpenCL community, and there has been talk about a new programming paradigm called Vulkan, which is kind of an OpenCL derivative popularly used to kind of develop data parallel applications in the context of Android like mobile devices, and mobile devices which subscribe to Android like operating systems. So, coming back to our ideas on heterogeneous computing, here we are talking about processors which are available in the system, and multiple of them are available and we want to use them efficiently, but of course this brings in lot of challenges. So, if I want to characterize a problem here, let us consider the classical architecture to application mapping problem. So, we have an application which may comprise multiple data parallel kernels. So, I am just trying to draw semantics of what we are trying to mean here. So, let us say I have a set of data parallel kernels with their dependencies, right. So, this is K1, K2, K3 and like that, K4, like this is the dependencies, and let us say so this is my application, and let us say I have a target platform where on the bus I have multiple processors, or let us open in terms of OpenCL, let us say OpenCL devices which are connected, and let us say so they can be of different types. This can be a CPU or GPU type device. let's say this is a GPU device, and let's say this is a CPU device, and it's running the host program, right? And so the objective is, suppose we have this kind of a platform, we have got this kind of an application, how to map this application to this kind of a heterogeneous compute platform. So I call it a heterogeneous compute platform because of this heterogeneity in terms of different devices that we have. There can be much more variety. For example, there can be, let's say, a device P4, which is some neural compute engine, some other kind of accelerator card which is there, which also understands how to execute an OpenCL kernel. So that's the important thing. We are subscribing to the idea that these are all different SIMD compute platforms. They can be CPUs, GPUs, some other accelerator cards. The constraint is all of them have on board an implementation of the OpenCL software specification, so that if this host program can discover this device, create a context for it, or create a context with multiple instances of such devices and dispatches kernels towards them, they will get executed, right? So that would be what we call the classical application to architecture mapping problem, restated in the context of heterogeneous compute. So the challenge in this case is to identify preferred task to device mapping, minimize the overhead due to data transfer and synchronization in such heterogeneous systems. So that is also very important. When suppose we consider, again let me just draw the figure that so if you have this kind of data parallel kernels and you are trying to decide whether to map them in a single device or across multiple devices, then the issue that may come, suppose you decide on a mapping decision that you map two of these kernels in one device and the other kernel in the other device. Then you have a data transfer overhead from this kernel to the rest of the kernels, right? But otherwise, or also the execution here has to wait for the execution of this kernel to complete, right? So you have a synchronization overhead, you have a data transfer overhead, and based on how you do the mapping, you have a overall throughput, right? So depending on which aspect you want to optimize, you have to choose what kind of task to device mapping you want to have, right? So in order to take full advantage of this heterogeneity, to gain performance in terms of performance or energy efficiency, the programmer will need to handle these challenges very efficiently. So this is an overview of the OpenCL runtime system, which we discussed earlier from our last lecture. So that was actually trying to give you an overview of the different aspects that are really there, like you have to compile the code, you have to create kernels, and then you have to orchestrate their execution across devices and handle the data transfer across devices. That's the overall job of this underlying runtime system. Now coming to this idea of heterogeneous compute. So sorry for this will be a computing platform here, and coming to this idea of heterogeneous compute, we are trying to give a very high level view here. So consider that you have a platform with multiple vendor provided compute elements. Of course, they are connected through some shared memory or through a bus based communication, they are connected, and you are using OpenCL to orchestrate the execution here. So one possibility would be, for example, you are building, we are just trying to give an example of how to build context like we have discussed earlier. So maybe I choose to create a context for this platform from the vendors of AMD. We are just again taking examples here, and then we create another platform from the vendors of NVIDIA. So again, I will just repeat, these are hypothetical, these are very hypothetical example. We are thinking that such a compute platform is available. This is a totally theoretical thing. It doesn't actually, of course, this kind of a platform will never exist. So maybe we can just think that, well, we have things from different vendors, and we are creating a OpenCL abstraction of this compute platform. Maybe we can create one context for platform 1, another context for platform 2. We go on to discover devices in each of the platforms. So, we will discover 3 devices here, maybe we will discover 1 device here, and we also go on to create command queues for each of them. This is like a very high level view of how things will look like. We are trying to say that this is heterogeneous because there are different kinds of compute elements which are present. The abstraction, the definition of OpenCL support things coming from different vendors, though again I will say that I do not think there are any example devices available where you have things from different vendors on the same die. This is very hypothetical here. So, I mean it could have been just a vendor 1 and a vendor 2. So, maybe we can say this is again from some vendor 1, and this is from some vendor 2, and you have created their corresponding devices. So, assuming that you have such a platform available, this is how you go on about creating contexts, discovering devices through the separate these commands that we have discussed and all that, so on and so forth. So, we know that there is this idea of command queues which can be created in a per device manner. Every device should have its own command queue, right. So, once those things are set up, there are a few restrictions we need to bear in mind. For example, a command queue can be associated with only one device. A single device may be associated with a single command queue, which this is a case we have already discussed. However, it may be associated with multiple command queues also in the same context. So, that can be another possibility. A single device may also be associated with multiple command queues which are associated with different contexts within the same platform. Because if you remember, we discussed earlier that even inside a platform I can create different contexts. So, maybe we can just go about and create one context using this set of devices. We can create another context again this set of devices. So, that would give me 2 contexts here, right. So, in that case I can have 2 different command queues associated with different contexts. Both of them are trying to access one device which is sitting in one of the contexts. Again, these are all theoretical possibilities that OpenCL would support. For example, again I will just repeat that you may not have this kind of a platform, but this is the abstraction that is supported, right. And it also depends on whether the vendors themselves have their own OpenCL implementations. Okay. So, you can also have this issue that there are different devices associated with multiple command queues which are associated again with the same context, right. And different devices which may also be associated with multiple command queues, and those command queues are associated with different contexts. So, let us just understand the differences. You have command queues, you have devices, and you have contexts. Every device needs a command queue, every command queue should subscribe to some device. We are trying to say what are the different mapping options there. I can have multiple command queues for a single device. I can have multiple command queues coming from different contexts, mapping to some device. They are issuing commands to some device in one context. I can also have in the same context multiple command queues, and I can have these multiple command queues associated with different devices, and I can also have the same thing from the point of view of different contexts. Okay. So, let us take these cases one by one. So, consider that I have multiple command queues with same context in a single device. Okay. So, essentially we are saying that multiple command queues can be mapped to the same device, but why? The fundamental reason would be that, well, the device is getting commands which are issued from the command queues. Now, inside, let us say these are in order command queues. So, you are issuing commands in order. If you want to overlap the execution from the different command queues, then you may have multiple command queues mapped to the same device. So, that let us say one command queue is enqueuing from one command queue has a read or write operation, and another command queue has a kernel launch operation, and they are overlapping on the device. That is a possibility. So, essentially what happens in this case, they are executing commands independently. Each of the command queues are throwing up their own commands to the device. Those commands are executing independently. I mean, among command, I mean, there is an independence among commands coming from different command queues. They allow applications to queue multiple independent commands without requiring synchronization, as long as the objects are not shared. So that's also one advantage, that if you have such multiple command queues, you are able to queue independent commands without requiring synchronization. Why? Because the moment you have commands in the queue, you have some ordering already being present, right? Now consider this case, you have multiple command queues with same context in single device. As an example of that, you can have independent streams of computation, and you assume that 3 independent tasks are there which need to execute on a device. Okay? So we are saying that you have one device, and I want the device available for executing 3 tasks concurrently in an independent way. So I will just set up 3 command queues in order execution with tasks enqueued in each of them. That would form a pipeline, so that each device executes the kernel code while the I/O is transferred. So let us say from one command queue I am issuing an I/O command, like I am issuing a read or write command. Parallelly from some other command queue I am issuing a kernel launch command. Since the device will have separate hardware for read, write and execution using the say streaming multiprocessors, these operations can overlap, right? They can be done concurrently. So this will help in achieving better utilization by not having the device sit idle and waiting for data, right? Because while it is while the copying engines are doing the read write operations, I have the device executing some other kernel coming from one of the command queues, right? So if I have this kind of multiple command queues within the same context, and they are issuing commands to a single device, this is how it helps me to overlap executions. It's just like a pipelining based speed up argument in computer architecture. So let's say command queue 0 is providing this command sequence: copy data to device, kernel execute, copy data to host, and there is the same sequence for another kernel, and those commands are coming from command queue 1. Similarly, I have such a sequence from command queue 2. When I have this kind of execution, and this execution sequence is going to the same device, right? They are going to the same device sitting in the same context, then I can see that this data and execution can happen in parallel. Copy data to host, copy data to device, and execution can also happen in parallel, provided you have got multiple copy engines which are often available. So one copy engine takes care of copying from the device to the host, another copy engine takes care of copying from the host to the device. So in that way also I can have this kind of overlapped execution. So that is the advantage in OpenCL of having multiple command queues with same context in a single device. So we can create such multiple contexts for same device on the same application, and but what if I have multiple contexts? Is there a benefit? Typically no, because it doesn't. So this is the other case where I have such multiple command queues, but the command queues are coming from different contexts. So the kind of overlapped execution advantage I get inside a context, that would not happen now, right? Typically that's why there is no benefit. It is useful when an application that use OpenCL for certain operations will also use some third-party library that also happens to use OpenCL internally to accelerate some algorithms. So you have one context for the application. You can create a separate context where you load that third-party library which uses OpenCL internally for algorithmic acceleration. So those are the cases where for providing support you can land up in this kind of a setting. So Coming to this programming of multiple devices. So, this is all about single device multiple command queues. Multiple command queues are sitting in the same context and different context. Now, let us talk about multiple devices. So, for that I will have two execution models. I may have two or more devices which work in a pipeline manner such that one device waits on the results of another. Alternatively, I can have a model where the multiple devices work concurrently, they are independent of each other, right. So, let us now consider different devices which are in the same context, and we have multiple command queues for these different devices. So, for multiple devices in a system, for example, a CPU and a GPU or multiple GPUs, each device will need its own command queue, right. So, you have a context where you have multiple devices and each device will need its own command queue. A standard way to work with multiple devices on the same platform is creating a single context, as memory objects are globally visible to all devices within the same context, and an event is only valid in a context where it is created. So, just to remember that if you have multiple devices, you may want to create this kind of a single context, because then the memory objects which you create before actual kernel execution, they are global inside the context, they can be accessed by all the devices, and same thing will hold for events that you define. Okay. Now, inside the same context, you can also have this sharing of objects that you define across multiple command queues, but it will require the application to perform appropriate synchronization so that dependencies are preserved. Now, event objects that are visible to the host program, they can be used to define such synchronization points between commands in multiple command queues, right. Like we have seen some synchronization examples earlier, but those were for a same command queue. We are just trying to say that since these synchronization events, the event lists in OpenCL, they are global data structures inside the same context, they are actually available across command queues, right. So, I can have events that have been triggered in one command queue, they can actually be used to trigger events in another command queue, right. So, if such synchronization points are established, then the programmer must assure that command queues progress concurrently and establish the correct dependencies. So, of course, like we have seen earlier, that using the event model, the event lists and triggering events, using this programming model to establish existing dependencies is something that is on the hand of the programmer, and the programmer has to assure that it really happens nicely. So, consider some examples now. For example, multiple command queues which are created with same context in different devices. So, you have one platform having one CPU device and one GPU device. So, you have this a devices array. So, what you do, by just giving an example of a similar code first, the difference only will be creating multiple command queues for multiple devices. So, first you discover the devices using this CL get device IDs. So, you discover the CPU type device and the GPU type device. So, and then we are assuming that we already know that in there we have this one CPU device and one GPU device. Then you create a context where you use up both these two devices. So, that is a single context that you create for two devices, right. And then inside this context, so then inside this context you will be creating queues for each of these devices, and that is done in the next two commands. So, you have CL create command queue commands here for creating the command queues for the same context, right. And then but one of them is for the GPU. So, as you can see that for the same context you have the two devices, this is the GPU device. So, for that you have Q GPU and similarly for Q CPU, and and then it will be possible using this programming model that for these two devices you can have overlapped execution, that is, you should be able to launch two kernels, so that one kernel is executing in the GPU device, the other kernel is executing in the CPU device, but they are sharing data through a memory buffer. So, it will help us to get the point that the multiple devices will be working in a cooperative manner on the same data, such that the CPU queue will wait until the GPU kernel is finished. So, as you can see from this dependency diagram, we have kernel 0 in the command queue. Kernel 0 goes from dispatch to kernel 0 starts running. After it ends, so consider timing here, right, in this axis. So, in the memory buffer, it is accessed and the data is written. After the data is written, you may have the data being accessed by the device 1, where the kernel was waiting, and it will start running. So, we know how to write such codes, and we'll go into looking into such programming models in a deeper way. Maybe we will end this lecture by stopping at this point of time, and that would be all. Thank you.